We'll cover the rest of the materials of the UART, which is mainly the RX part of it, and the tutorial for UART is due 27th, right, Friday this week. There will be another one on Thursday. It's a new one about the soft core. It's pretty exciting. It's programming, putting all the assembly coding into the ROM and synthesize everything in Vivado. And it's basically a little microcontroller being programmed in FPGA. And this will probably take, I think the lab takes 2 weeks. The tutorial is a little bit more than a week. Also 2 weeks. So next week we'll do our midterm exam, right? There will be a review next Tuesday. And the lab today is about the USB. I don't have actual keyboards, and I'm looking at the keyboard to see if we can just unplug it, but make sure you plug it back in. I mean the lab probably is easier. So I have to use some of the keyboards in the lab. And today there will be a quiz. We'll start working on the quiz at 9 a.m. So let's look at the UART tutorial one more time and scroll to the bottom of an RX receiver. Also look at the in class. I think I have something over there. But there are two questions on the in class number 7 from last time. You guys haven't turned in yet. So there are 2 questions we didn't answer last time. And you can see the first question is, I think one of them, right? One of them is why we counted to half of the ball timer number. Remember with the ball timer? The ball timer is a count. This is 100 million counts per second, and this is bits per second. So this divided by this is giving you what? Counts per bit. So counts per bit is just perfect dimension because we need a counts per bit, which is actually counts, right? Every bit to stop the counting, right? So that's how we define the baud rate. The 100 megahertz clock is given from it's a resource on the board, which is use that one as a timer. And the question here is why we time it to half of it for one of the states. So Rx is shorted to the Tx of the transceiver, of the transmitter. So whenever Tx pulls it down, right? So you see the timing sequence over here. This is controlled by the Tx. So the Tx is sending and the receiver is just passively receiving, right? It's not controlling, pulling on up and down the transmission line. So it's basically just being put down by the Tx. Okay. And that's the starting bit, right? The starting bit is a 0, logic 0. And the reason that it should count to half of this total count, or the 1 counts per bit, is that if you do it here and then after this state, you keep doing that the standard number of, or the baud timer, or the standard number of counts per bit, you will be able to sample in the middle of the data, starting from the halfway of the starting bit. Does that make sense? It doesn't. Let me draw it here for you guys. So look at these. Look at this one. So count to 50% of the baud timer, starting from where? Starting from the moment that it pulls it down. Is there any difference on the time? Maybe, but the thing is, the clock can run really fast. if there's only a little difference or error just because of the period of the clock, it probably doesn't matter that much, right? So we can, because the original clock can see the pulse edge of the clock is running really fast at 100 megahertz, so you can consider that it's almost getting synchronized to whatever the signal here that you need. It's so fast, right? So whenever this guy is being put down, TX, RX, right? That's the start bit. And after that, you have the same width of all the bits being transmitted. It could be 1, could be 0. I'm just drawing this. Right? This could be so this number of counts or this period of time requires a ball timer. This number of counts over here, right? And you define one little state at the very beginning to count halfway of the ball timer, and then you start doing the full one piece of the ball timer. And you can always sample in the middle of the data, because sometimes there are rising edges, falling edges will give you uncertainty of the data. You can sample, you do want to sample over here, right? And depending on the quality of the data, I mean, for this kind of slow, super slow motion data transmission, right? It's so slow. It's only 9600, or sometimes 19200 bits per second. Right? It's still very slow. So compared to the quality of the edges, I don't imagine that you will be able to even visualize or even see this rising edge, falling edge at all. So it's not significant. I'm just drawing this to exaggerate the issue here, right? So the goal is to sample in the middle to get rid of the area that has the edges, right? So you can directly sample in the middle, because either 1 or 0 instead of anything in the middle. So the goal is to sample in the middle. That's why we want to count to the halfway first, and then we keep counting the one piece of ball timer every time after that. So you can see the states would never. So we have a ready state for the receiver, and the ready state is going to check your RX bit, keep waiting here, and whenever this is getting satisfied, which means the TX just put it down, then move to the next state next time, right? Okay, so you want to reset the bit index as well. So whenever it gets into the start state, it counts halfway, right? It counts halfway, which is just the halfway of the starting bit, and like what I just described. And you reset all the timer and ready and arrows the flags, and then go to wait, right? Go to wait. So wait is just waiting for the ball timer, which is the one piece of the number of counts for one bit over there. So if this is not getting satisfied, it will never enter all these conditions, except the else, right? So just keep adding timer, incrementing by 1, and whenever this is getting satisfied, which means the timer's up, you clear the timer, you go. So see if you already transmitted all the A bits. If not, go to receive, right? Start receiving that bit. If it's ready, finished all the A bits, go back to ready. Go back to ready. So ready is waiting for that pull down again, right? So it's the starting bit. It's waiting for that again. All right. And now, if it's not ready yet, it's not sending all the A bits yet, goes to receive. You'll see RX, this little bit is directly being given to the RX data, which has the index being incremented every time, and then incremented. So the thing is, if it's receiving the 9th one, it's a little bit different. I think this is one of the questions on the in-class number A. So this receiver, can you directly use this receiver with the TX transmitter that we just learned at the very beginning of the tutorial? Could you directly just use this one with that one? Remember the TX. Look at the TX. How many bits per message for the TX? Starting bit, stop bit, and 8 bits, a byte in the middle, right? That's the entire message. Is there a parity bit over here? Nope. We're not creating a parity at all, right? It's just a very simple TRX-RX transmission. But for the RX module, if you look at the experiment here, what are we doing with the RX? Think about it. If you are the instructor, you are designing a experiment with RX. How do you verify the RX logic or the digital block of the RX on the IPGA? What are the transmitters that you can send to the RX? It could be an internal RX, TX, but you can see that we are definitely using a serial monitor. You have used the serial monitor for many times, right? In the microcontroller class. The serial monitor is able to do TX and both TX and RX. Alright, so when you use the Arduino, you plug it in and open up the serial monitor, it's able to read, remember the serial dot print, right? Print line, these kind of commands. So that is actually a TX command. Right, it's a TX command from your microcontroller, right? It's a TX from your microcontroller. It directly send. I mean, even though it's called a print, but actually it's sending, right? Sending from the microcontroller to the serial monitor. So it's printing to that. So it's basically using the TX port, right? Using the TX port. So for this one, we are doing that in the opposite way. So the serial monitor can also print letters to your microcontroller, to your receiver module, since you are programming a RX module, so it's actually receiving things over, from there. So you can see that we have a top. Let's see. There's a demonstration video. Where is that one? That video is probably deleted. All right, so there's no video over here. This is just showing you that I think the video is not uploaded, but that's fine. So here's a block, right? The block. A diagram of all the modules. So RX modules over here, there's 100 megahertz from the serial monitor. So you can see it's from the USB. It's sending to the serial module, and you need the top to cover it as well. And here's the top. Okay, so top has pretty simple states, right? So it's waiting for see if the data ready is done or not. So it's a actual layer outside of the module of the RX to see if the 8 bits are being received already. Then it's gonna do another one, right? So it's a control layer outside of it. You do need that because the RX module itself wouldn't check that readiness. It's just a flag giving a flag. And so you see here, after it received the 8th bit, it goes to check. And this is a really interesting statement or condition here. It merges both. The first is checking the parity bit, and second is trying to look at the operation if this is true or not. So it's question number 1 on the in class. So which line of the code will get you the parity bit of the 8 bits received data? So from the receiver's module, this is a vector, right? And Verilog allows you to directly put an XOR operator in front of the vector, and it's gonna do a bitwise XOR to all the bits. Okay, it's very efficient. So it does this operation first, and that one you can say it's returned, but it's not actually returning. But there will be a final result after this, right? After this, You can consider this as being return result of this operation. And that one is being compared to this bit. And this bit is a parity bit. Because the bit 8 is actually the 9th bit, right? It's outside of the byte message. Okay? So that is why this one cannot be used, directly used to interface with the TX module, because the TX module doesn't have this bit. Okay? But the TX of the serial monitor does have it. Why do I know that? Because you can see if you open up the, I think, what's the name of the serial monitor? PuTTY? Is that a PuTTY? Oh, Terra term. It's a different one. But I think they both do the similar thing. If you can use this Terra term as terminal, serial terminal, and you can follow the same interface, the same steps over here to set up the parity, right? So I'm setting up the even parity bit generator. It's even parity generator because this is the sender as a sender. So the sender, the serial monitor as a sender, it should generate the parity bit. Okay? And it's an even parity generator. So my quick question for you guys is, if it's an even parity generator, how many ones do you expect in the total message, including the parity bit and the message itself? Do you remember that? It should be even number, right? So what of the message though? The message itself, the data itself, should be odd, right? Yes, should be odd. And then your parity bit generator should generate one bit to add it to the odd number of ones to make it even, right? So eventually, whatever the message being sent should be even number of ones. All right. So in that case, in your RX, right, when you're checking it, why this works for that kind of logic. So you can see if this equals this, then it's ready, right? Otherwise, it's sending a 8-bit binary X, just uncertainty, right? Just nothing. Doesn't matter. You can define the error message, whatever you want, right? So if it's not right, if it's not correct, I'm just overriding all the data bits with the X. It's just high impedance. It's nothing. So I don't want to use the data. Just override it. Okay. So which means this is wrong. So which means if this is equal, it passes the check. Why? This is a parity bit, right? This is a parity bit. If this is 1, what does that mean? If this is 1, if we do a bitwise,
that means we have an odd number.
you have an odd number ones over there, right? Odd number ones. So if this is 1 and this is also 1, they are equal, right? So in overall you have even number of ones because this is 1, this is also 1, right? This is odd and this is 1, so you have even number of ones. Everyone's happy, right? Otherwise, if the zeros is also 0, then they are still equal. It's still even number of ones in total, right? It's just so efficient. A little trick here, okay? It works. Anyway, so if they're not equal, which means you're not getting even number of ones for the whole message, and it should go to the else. Should go to the else block over here, right? Make sense? Okay. Question number 2. Oh, I think there's another one over here. Another question is the last question of the in class number 7. In class number 7, there's one more question over here. So, what is happening over here for this line? What is this guy doing? So you can see the receiving top is really simple. Really simple. First, it overrides the baud rate, right? 19200 instead of using 9600. So I've used a parameter in here and it follows a certain order, right? Remember last time we were talking about that, why it knows that which parameter to override. It follows a certain order. You could, in your top, you could do this multiple times, like hashtag and parentheses. You can do this multiple times. But it just follows a certain order, right? So what kind of order you use for the top, it follows the order in your sub module, like the orders that you declare the parameters. Since we only have one parameter, so this will be the one to be overwritten. And this would not be overwritten because the local parameter is a constant. It's not changing. You cannot change it. But parameter can be changed by the top. So you can override it. Right? So this is being overwritten. Even though it's 9600, but your top is redefining that baud rate to be something else. Okay, to be something else. So in that case, we don't want to use numbers for these, right? For here, we only need to change. We only have a number being defined to a variable, and for all the rest of the script, we just directly use a variable. So if this is being overwritten, everything will be updated as well, right? So you don't want to directly use numbers. You want to put a 9600 over here. It won't be updated by the top if you put a number here, right? It has to be a variable. And you can see that the top has these ports, right? These ports, clock, no problem. RX, no problem. Data, it's just data, right? It's just data. Parity bit, just one bit. Ready, error, okay? So error is an indicator. Error is an indicator. And the indicator is being created by here. It's just an if statement. If it passes error is zero, is the original value declared. And otherwise, I put a 1 to error. So you can use this error interface with one of the LEDs on the board, right? So here's the error bit. You probably will never see this error bit to be lighting up, right? You don't have that kind of noise to change to toggle your message bits. I don't think it's gonna work. If you find a way, let me know. I'm very curious because this will never be lighting up. It's always off. It's always right. Okay, it's just so reliable, right? It's so slow. This is not really easy to get an error bit somewhere. So that's the error bit being directly shorted to one of the LEDs. And the way we did that is error, well, let's see. Here, right? So we did a concatenation. We have the output, parity bit, and error bit, right? So to be placed in these 10 bits of the LEDs. Okay? And you can see this one is really simple. Even though it's LEDs, it's 6 LEDs, but it can do you could increment the LEDs by a binary number by 1. It's really interesting. So it's being treated as a vector, even though these are LEDs, but it's just being treated as a vector is a binary number. So you can definitely add a 1 to it. So what is this doing is these 6 bits, LEDs of LEDs are indicating like how many bits, how many data has been received. You can see every time it enters here, it forms one total data. It increments the LEDs as a binary number by 1, right? So what's happening is, you can imagine it's starting from 00001, right? And then after it received another bit, another byte, this becomes 10. See? And 11, 100, and 101. Just keep incrementing by 1 until it reaches the maximum, and it will reset to 0. So it's just a counter to show you how many bytes have been received by the RX module over here. So these are the data. That's the parity bit, error bit, and counter. Okay, it's a counter. That's everything about the RX module. So I think that's everything about in class number 7. Did I miss any questions? I don't have a copy here with me today. Did I miss any questions in class number 7? No? Okay. So now let's jump back to in class number 8. The first question already answered. The second one, does the TX module and the tutorial have the same length of the message? Nope, right? So we also answered that because the RX module has a parity bit, but the TX doesn't. Okay. Explain how. Okay, now it's the lab. From question number 3, it's going to be the lab for today. Lab. Goes to the lab. USB. Have to use a keyboard. USB controller. Okay, USB controller. So you can see there are the codes for every single key on the keyboard, and they look similar to the ASCII code, but definitely they are not. Okay, just to let you guys know, they are not ASCII code, and it's very simple. They are just different code, right? Different code for each key. And the transmission protocol in the old days, you probably haven't seen this before. The PS2 interface, not the PS2 itself. The PS2 interface, and the PS2 itself is way more cooler than this. Have you seen this one? This kind of interface in the past? The really old. Yeah. So these interfaces use the PS2. Whenever we talk about the new interface, it's just a new protocol, right? It has a clock, has a data line, and it's also a serial communication port. Just to let you guys know, it's also serial. Definitely, it's a serial, right? It's just not too many ports, not too many pins. Have you seen any parallel pins in the past? No internet. Okay, so the parallel pins appears at the super old, like from the 1970s or 1980s. So this computer can see a very long port, has like 32 pins over there, or how many pins? 16 pins sometimes possible. Parallel pins are fast, but it's taking a lot of pin resources, right? Things like this, like this. I'm not sure if this is a parallel pin. This is a parallel port. Okay, very bulky. Okay, you can see the PS2 only has a couple pins over there. It's definitely serial, of course, right? Definitely serial. So it's just one wire for data transmission, following a certain timing, right? For a certain timing. We don't have a PS2 port on our IPGA board, but we do have a little microcontroller which is able to convert your UART to PS2. Right, so this, if you look at your Basys 3 board, just next to the USB port, there's a chip. It's a microcontroller. It's a PIC 24FJ, whatever. It's a pretty advanced microcontroller. It's able to provide you with the PS2 interface. But we don't worry about the protocol. The reason for that is, you can see this is a constraint file of the IPGA, and it has a PS2 clock and PS2 data, and these two pins, and every single one is one pin. You agree with that, right? Remember, in the constraint file, every single port is one pin. It's actually one physical pin of the microcontroller, of the IPGA. All right. So this is two pins, right? Two pins communicating with the microcontroller. The microcontroller converts your this to UART, and the laptop converts the UART into USB. So it's a lot of conversion. The USB is very complicated, actually. It's really easy to use. It's super complicated. For the timing wise and everything else, the protocol has a lot of like acknowledgement and receiving. So we don't really use the USB. It's not really a USB protocol. We always convert it to UART, right? So it's called serial. We always do TX and RX with the laptops. So the USB port is able to simulate a UART transmission, and eventually we just have a TX and RX communicates with the laptop. So you can see the thing is, you got a UART here, right? UART here, and UART converted to PS2. Okay, convert to PS2. So the PS2 output, I don't know which pin, I don't have to know, right? So there'll be two pins from the microcontroller. The PIC microcontroller has two pins. One is the PS2 clock, one is the PS2 data. Just two pins, a clock and data line, to be shorted to these two pins of the IPGA port, of the IPGA chip. Okay, and that's called the HID port, USB HID port. HID, what's HID here? Human interface devices. So it could be a keyboard, could be a mouse, right? Mouse or keyboard. So if you use this microcontroller combined with a little module, the USB module we're going to cover for the tutorial. You put these onto FPGA, and you will be able to design a little human interface device interface from the FPGA, which is really cool. I mean, you imagine how you would do that with the microcontroller with the Arduino. It could be challenging, I think, if it's just an Arduino. So this is the strength of the FPGA, just so flexible. And Arduino, if you want to use Arduino, use a C language to describe the hardware like this. You'll put a lot of lines, and it's odd, right? You're writing a C language and combine with interrupts and delays to form that timing. It's not really convenient. So you can see sometimes you prefer FPGA, sometimes you prefer microcontrollers, right? So for such a controller module, if you have to use a microcontroller in the future to design the instrument to control human interface, human interface devices, there must be drivers, right? So dedicated digital chips that I can buy that have all these controllers inside. So these were designed by other digital designers, so you don't have to deal with it by yourself. Right. So let's look at the sub-modules, the USB here. Even though it's called USB, it's not, okay? It's just dealing with the PS2 ports. That's something you need to know. So it's a USB to UART to PS2 converter. So eventually, it's not a USB protocol. You only care about the PS2 data, okay? And the PS2 has the data, has a clock, so definitely there will be a timing diagram. So the timing diagram looks similar to this, something similar to this, okay? You can see that it's all the serial ports, and when you learn a lot of them, including SPI, you'll find out that they kind of similar in a lot of ways. So it starts with a 0 as a start bit. It pulls it down, right? Pulls it down. And the clock is a bit different. So the clock is not synchronized with the data's edge over here. So what this does is the negative edge of the clock will sample it. The negative edge of the clock samples it. Okay? So that's a protocol directly from the chip. If you are doing human interface, it's directly being sent from the data, right? From the port. So this is what you are going to expect. Okay, going to expect. And we need to write it or design a certain timing in your sub module to sample the data. So that's the two modules. The only two modules we have for the lab. Okay. So the one on the right hand side is a core, is a sub module. On the left is a top, or it's application. Right. It's application. So line number 39 over here, it asks you to explain why this works, right? Why this works. So we have to start from the very top first, okay? So you can see that this guy has a negative edge of the clock. So it's actually forming this, it's a PS2 clock. Okay, it's a PS2. It's not the clock, 100 megahertz clock from the FPGA board. So this one is a clock from the PIC chip. The top, see, the top here has the clock port and the data port. So these are the physical ports of the chip, of the microcontroller, outside the microcontroller. And this port is directly shorted to your sub module. So basically you're monitoring that sub module's clock, right? Whenever the negative edge arrives, I sample it because of the timing. Okay? So the PS2 clock and the PS2 data, these are already formed by the keyboard. It's already being output as the output of the PIC microcontroller. If you look at the diagram, probably will make it a little bit clearer. So keyboard directly connect to the FPGA through the USB, and then interfaces with the PIC microcontroller, and then these are the two pins, physical pins of IPGA. Okay? Is there a desktop involved in this experiment? No, it's directly keyboard to the USB, right? To the USB of the Basys board. So it goes this way, and these are the two physical ports already, right? It's the two physical ports already. And no matter what, as long as you power up your IPGA, your keyboard is being powered up. There's no actual power, right? So the IPGA is being powered up. The 5 volts will be delivered through the USB to the keyboard. The 5 volts, right? USB is always 5 volts. They have a common ground. They have everything. There's no desktop involved. It's just the laptops. The laptop's USB from the small USB, and then you have the bigger USB, standard USB port is connected to the keyboard, right? So the laptop's 5 volts delivered to the Basys 3, and then through the Basys 3 board deliver the 5 volts to the keyboard. Okay, so these two, as long as you power it up, the IPGA board, these will start streaming, right? Start streaming. At least the clock will start streaming. If you don't have data, don't have any key being pressed, there won't be any data, but there will be a clock. The clock will start pumping things in, right? So that's directly shorted to here, and you are actually passively detecting that. Whenever there's a negative edge of the PS2 clock arrives, you start sampling the data, okay? Start sampling the data, which makes sense because the timing diagram just tells you that, okay? As a negative edge arrives, you start doing that, starting from the start bit. Okay, so starting from the start bit, see? The first time the negative edge of the clock arrives, I'm at the ready state. I keep checking. If it's 0, it's checking. Whenever there's a 0 shows up, which means that it's a start bit, right? And I clear everything, and I move to the receive state. So whenever it's at the receive state, it keeps receiving until it reaches number 7. I will start receiving the parity bit. Okay, I receive the parity bit. Otherwise, just keep sending the PS2 data into this vector, right? So until the 8th bit, and increment your index. Just keep doing that. Keep placing all the bits into this vector. Okay. And whenever it's all done, it comes to the parity bit. But still using the same data line, you just give it to the parity bit variable. So that's also being stored over there. And move to the stop, right? So it's done. Whenever it's at the stop state, definitely you want to pull it up. It's very similar to the UART protocol. You pull it down at the start bit and pull it up as a stop bit. Okay? You pull it up. So put it up first and then put the state to ready and then give a 1 to ready. So it's important because you want to tell that the data is ready to be used. The digital transmission is really quick, transmitting really fast, right? You have to know that, you have to indicate that, hey, everything's ready. I'm not doing the transmission anymore. This is the byte. It's ready in there. Okay? So it's being stored in the received variable or vector. It's being stored in here. So you can do a quick parity checking. If there's an error, do this. If there's no error, give it to the output port. So now let's see if this one makes sense. It's very similar to the RX module. Do a parity check. Right? So this condition, if this condition is satisfied, there's an error. Why is that? It's doing the same thing. It's doing XOR logic, bitwise XOR for all the data being received. Right? And how many bits are in the received? It's 8 bits. So this is only the data. There's no parity bit, right? So received, this variable has all the data in there. Do a bitwise XOR logic. If it has odd number of ones, right, this becomes 1, and you do an inverse of it, it's a 0, right? It's a 0. And if 1 is not 0, then there's an error over there, right? Wait, is that something we want? Is it even parity checker? I believe so. Okay. Think about that and organize your language over there for the question. I think this is question number, which one? Number 3, right? Number 3. So if parity is 1, which means the data has odd number of ones, right? Has odd number of ones. So you can form an even number of ones overall. Okay? Then the bitwise XOR should be 1. So if parity is not 1, then there's an error. So for example, we have odd number of ones over here, right? And then this operation give you a 1.
So that'll be 1, and then it's a 0.
That's a 0.
And then parity is not.
If parity is 1, it's not 0, it's actually correct.
So parity, so is parity 1, is that for odd? You're doing an odd check?
How do we determine?
How does parity set?
Yeah. Is this data being sent from the keyboard?
It's just coming from the top module, so probably.
Let's see. Seems like it's a odd parity instead of even this time.
So it just depends. If you set parity to 1, then you're doing an odd parity check. If you set parity to 0, then you're doing an even check, right?
Yeah, but parity is the data, right? It's the data being received. It's not set by itself.
I thought that was received.
How was that received?
I don't know.
Yeah,
Parity
this
received.
is from. Is parity parity is not a port.
It's PS2 data, right?
Yeah, parity is not being. Yeah, it's a PS2 data, right? It's one of the data bits, right? But yeah, so the one of the PS2 data bits is given to parity, right? So it's actually from the port, from the keyboard. It's from the keyboard. So depending on the setting of the keyboard, actually, right? I don't see any parity setting for the top, from the top. It's basically just a serial data transmission. But the serial data transmission doesn't have the extra bit, actually. So
I should scratch this question.
yeah, I think this is a bug from the textbook's code. I think this is from the textbook. Parity is not being used at all. Is that right? If you have a different opinion, let me know after the class, right? I don't see the parity is being used at all. Because these are just a byte. There's no extra bit. Where is that extra bit? It's not actually, it doesn't have that extra bit, right? So which means it would not enter here.
Well,
It would not do it. But why it's
below this code, you say it's helpful to know the timing diagram of the PS2 data, the PS2 clock. If you scroll down a little bit, and then you show the timing diagram. But then you say the PS2 data is 1 bit in the code.
yeah. That's interesting, right? Because you can see the data is being formed. Let's look at the top so we know what the data are, right? So what's the data here? So the thing is, the keyboard follows a certain protocol. You press it, it shows a make code and then the break code. So the make code is
Parity is, it just grabs the 9th bit, so it loads those first 8 bits. and then as soon as that's over, it just goes back and grabs that parity bit. And that's
Okay.
what parity is.
Yeah, so it does it by itself.
Yeah. So it just grabs if the parity is 1 or 0. So then you're doing an
The thing is, if you look at the length here, it doesn't have the room for that parity. It probably automatically does it.
I think
It
it's
just,
I think that's
just,
what-
well, it just goes on the next clock cycle and grabs the next thing.
Yeah. I think that makes sense, but let's assume that's what the case is, right? But the data itself, it doesn't really have the room for that.
so the
It's probably it's just sent by itself, right?
What?
so the even odd
No,
parity
if you-
is just determined by our protocol. We don't have any say in it.
You gotta generate it, right? You have to generate it, but now it's the sender is a keyboard, so maybe the keyboard generates it. Let's look at this first. Probably I just forgot something. Let's look at this first. So when you press it, it forms a make code. So this is a package formed by the keyboard, right? By the keyboard. You press it once, it forms the make code. So the make code first and then break code. The break code has a little mask over here, 0x F0. The thing is, it's sending that whatever you press, the key code, you keep sending that continuously. So only detects it's only one press event because you have a break code over here. You know what I mean? So when you press the key on the keyboard, it's gonna start sending that key code continuously. See here? That's a key code. For example, you press 1, right? You press 1 here. It's gonna send a 1x. 1.6. So 1.6 will be sent continuously, and your Windows operating system is able to detect it, and won't recognize that as a one press event, because there's no break code. So when you release it, it inserts a 0x F0 in there, and then followed by the key code. So it makes it different. You can imagine if you keep pressing it, shows all the key code, right? If you don't release it, it's always the key code. Your operating system is able to identify that as just a one press. There will be a certain time delay when you are trying to press it over here. It's a little different, but see, there's a time delay, right? If I press R here, there's like a 500 millisecond time delay. You know what I mean? See, R, right? So the first one, after the first one, there's a little time delay. So operating system is able to detect that. So you press it, your finger is so slow, but when you press it, there's probably thousands of key code being sent to it. If the operating system detects it, there's a certain code, a driver inside laptop. This is not something we are dealing with, but it's able to detect that and give a time delay that shows that, hey, this guy is still putting his finger on it. Then I will just directly replicate that press, right? It just shows that this way. So they just want to have multiple replicates being typed. Okay, that's a different thing. However, if I just press it once and release it, you can see just one R here, right? Just one R. So I'm pressing the browser's box over here. If I just press it once, right? Press it once, it's only detected one, right? So depending on your fingers' speed, usually when you are typing, I believe your fingers press event is faster than 500 milliseconds, right? So it's usually probably only 100 milliseconds or so, like this. Every time you press it, release it, it's probably only 100 milliseconds, or even maybe 200, depending on different people. If your finger is too slow, when you're getting 95 years old, you are typing multiple letters every time that happens. And so the keyboards are not designed for these people, probably. It's not really friendly, but you can have an app just for old people. So you are not typing multiple letters at each time. But the thing is, it has a very sweet duration that only allows you to type one letter instead of have a lot of replicates. So I think that's a little time delay over there, a little mechanism being designed in the operating system. So the thing you need to know is it's trying to differentiate between a continuous press and a single press. So it's outputting one letter or multiple letters, right? So the way they do it is to plug to plug in the 0xF0 in between the key code. Okay. Keep in mind, it's not always just one key code. Whenever you press it, there will be thousands of key code being created. But whenever you release it, right? When we release it, there's just one 0xF0 being plugged in the middle to show that this is one release. So this is being considered as a break code. So it's going to be a 0xF0 followed by the key code. It has to be the same key code, right? It has the same key code. So it's identified as the same key being pressed and released. That's the whole event, right? Pressed and released, the whole event. So so for the definitions, you can see there are a lot of like key code, make code, break code, right? So break code is a key code. Make code is a key code, the first one, and then break code consists of 0xF0 and a key code. Make sense? All right, so it has to detect a previous 0 and current 1 in order to know that it's a one data transmission is done. So one byte transmission is done. So it's actually looking at this little rising edge over here. Okay, so this little rising edge, so you can see previously it's a 0 and now it's a 1. It's a rising edge, and this is defined in your sub module. Why? You see, whenever it's getting started at the starting bit, it pulls it down to 0, and whenever it's done, it pulls it up to 1. Okay? So when you put it up to 1, it's at the stop bit, which means it's done. All these data bits are already stored in the vector. So you are basically looking at this rising edge. Okay, rising edge. And that rising edge will be picked up by the top. So we are doing a previously check and current check. It's a 0 and 1 in order to make that happen. So if a 0 and 1, which means that byte is already transmitted or being received, it's available at the data, this port. I want to assign all the 8 bits to received to this vector, right? So you can see I have a 24 bits over there. Why 24 bits? You can see 8, 8, 8, right? So it's 8 bits. It's 8, 8, 8. So this is from bit 16 to bit 23. This is from bit 15 to bit 8. This is from bit 0 to bit 7. And the first one will be the key code. It's the data. So the key code is being placed over here for the upper 8 bits. And then move to the next one. Has to be another data with 8 bits again. And that is being placed over here. And what is that data? What is that one? What is this one? Data, right? Data is just a storage space. It doesn't really know, as long as the byte will be stored over there, right? So after the key code is being received over here, the data is being received over here. It's just the data, right? You don't even know, but most likely, most of the chances, it is the key code again, because your finger is so slow, right? When you press it, it's sending thousands of key code to it. It moves to the next state to detect if that data, the second byte, is F0. The thing is, if you don't release it, it's not going to be F0, right? It's going to be thousands of key codes. But whenever you release it, it detects F0 and then moves to the next state. It's just perfect. I like this design a lot. So it's waiting for there. It handles your finger, your slow finger, right? You just press it. There'll be a lot of key codes, then, which is fine. It's still at the release state, but you are not necessarily having that release code, right? You just keep staying here, keep checking, release, not releasing, just stay, right? Whenever it's getting satisfied, move to the next, and then detect the rising edge in order to receive the next byte and put it in the received vector. So now I have all these 3 bytes a key code, a break code, 2 bytes over here, and then move to the check. So look at this. So the check is not parity check for the top, right? So this is just a check for if the certain keys are being pressed, right? So it's just showing you these key codes, right? Because there's no way to look at it. So you are just directly putting that key code in your top module. And these are the key codes for the keys. And if this entry, if it enters this entry, it toggles one of the certain LEDs. So what you are looking at is you press a key on the keyboard. Since I only defined these keys, right? 1, 2, 3, like 8 keys from 1 to 8. If I press any of these keys, it's going to toggle one of the LEDs over here. Okay, it's going to toggle one of the LEDs over here. That's how you verify your key code. Okay, verify. Because if it's not a key code, the certain key code is not sent to the FPGA, it won't enter this entry. These are the certain names of the key code. It has to enter it first in order to toggle that certain LED. So it's a really legit way to check the key code. So it's only checking the lower 8 bits, but you can see you have 24 bits over here, right? So is this the first key code really being used anywhere? It's not. It's not in here, but it's probably will be used for somewhere else. You stored it at the upper byte, you never use it here actually, right? And this is used for the condition checking, and this is eventually used as a data, and this is not actually used. This is not actually used at all. So you placed a byte over here, and you never used it in this tutorial. Okay. Anything else? So there's two tasks. There are 2 tasks. The first task is just repeat whatever I showed you guys over here, right? Just a keyboard, connect to the big USB port on the FPGA board, and the mini USB is shorted to your laptop to power it up and for communication as well. You keep everything powered up and start pressing the keys over there. So it should be able to duplicate it, simple, and so given, so it's only 10 points. And for the second task is 90 points. It's asking you guys to design a test bench and connect your TX module, right? So you press. So it's basically you still have this one connect to the laptop, right, or desktop. You press the key through the USB here, right? So you press the key code comes over to the PS2 data being transmitted to the receiver. Here, the receiver wrap it up into the through the TX module and send it through the TX module to the serial monitor. You know what I mean? So you are putting a TX module over. So one little thing here. Sorry, I may have had a wrong figure here for you guys. So this is not a PS2 controller. Actually, this is a UART to USB controller converter, right? So the PS2 is actually the next one. See? That's the PS2 microcontroller because that's a big USB connect to the keyboard. Not this guy. This is a USB to UART. Okay? This is a PS2 microcontroller, the PIC 24 something. All right. Task 2, is that clear? Task 2, what you are going to do? Keyboard comes over here, convert to PS2 data serial, get into the FPGA. The FPGA has a receiver, a byte received, and you design a little TX module of the UART to receive that data and throw it to the UART over here. So USB receive it, and your computer is able to detect it. So the serial monitor should display all the letters you typed on the keyboard. Okay? This is pretty amazing because you guys are designing a little keyboard driver actually. right? So it's directly keyboard, type on the keyboard and then directly display on the monitor. Like a 1997, 9077 probably, 9077 typer, printer, whatever. You can type over there and this gonna display it right to the monitor. Anyway, so this is just a 90 minutes, 90 points for a 3-hour lab. Should be pretty straightforward. Now we can start working on the quiz. Did I ask all the questions? Answer all the questions over there on the in class? Number 4 are the make code and key breakcode types of keyboard scan. Yes. So these are all called scan code. Okay. It's another definition. So make code, break code, they are both called scan codes. Scan codes. Yes. Okay. And number 5, is a keyboard key code the same as ASCII code? Nope. Does PS2 start with a 0 or a 1? A 0, right? The start bit is 0 bit. Number 7, receiving every bit of the PS2 data is synchronized to which clock? Definitely not a 100 megahertz clock, right? You guys know the answer, hopefully. Number 8, what's going to happen if the key is pressed and not released? What's going to happen if the key is pressed and not released?
The keyboard will just keep sending the make code.
Yes, we'll keep sending the key code. We'll keep sending the key code or the make code.
But our code just throws away the make code, key code, so.
Mm-hmm. And would that mess up your received code? Why or why not?
No.
Okay, because that's just the I think it's more complicated than what we are looking at. The operating system is able to detect it and just keep. It's probably controlled by the software, so
Yeah, it stays in the
stays the same, right? So it has a little
extend loop or
Yeah.
state.
Yeah. No, that's a good question, right? Should we try it over here? If we keep pressing it, are we going to show that in our monitor? Because this is not controlled by the operating system, right? It's a keyboard directly send everything to the serial port. So what's going to happen is, if your digital block doesn't have the mechanism to handle that,
But that's what the extend state is, right?
that's extend state. That's actually right. So probably you are going to keep getting that being sent to the serial monitor. You will get replicates, I think. Right? Try it in your serial monitor. Yeah. So the answer doesn't matter as long as it knows what's really happening. Number 9. The key code in the make code area used in this FPGA application. The key code in the make code area used in this application. Why it was placed in the make code area? My answer is it was not used. The key code in the make code area. I don't know what I'm trying to ask over here. The key codes are sent twice, and one is the key down. I don't know what I want. This is a question. I'm sorry for that. Doesn't matter. Whatever you put on there, I wouldn't take points off. Let's see. It's not used. Yeah, let's skip that one. Don't worry about that. Determine the user. Okay, that's all the questions, and I'm gonna give you the quiz.